Welcome. Today, we'll begin looking at the second approach to solve problems of this kind, to analyze situations of this kind, and so on and so forth. Uh, to recall, we are looking at momentum flux. We said even earlier while doing mass flux, there are two major approaches to solving problems. Here, first the problem needs to be posed, the situation needs to be converted to an appropriate problem needs to be posed, and then we can solve it using these two broad approaches. One was called the shell balance approach, where we wrote balances over a differential shell or a representative shell which depended on the geometry of the system. The other approach is the equation approach, the conservation equation approach, the equation of continuity, mass conservation equation for the earlier flux, the mass flux. In this case, it is momentum balance, or effectively second law of motion, Newton's second law of motion, or the same thing is called equation of motion in this case. So let us first derive the equation of motion, and then as it happened in the mass flux case, you will find that it simplifies the solving of many different situations. Of course, it has some limitations, the same limitations as earlier. Whenever there's a change in geometry of the shell, if there's a variable, let's say a diameter or something like that, these equations or some of these equations may not be applicable. With that, let us begin today's main aspect, equation of motion. The shell balances can get cumbersome, especially in the cylindrical and spherical coordinate systems. Let us derive a reasonably general equation of momentum balance. As I said, strictly Newton's second law. The equation of motion, what we're going to do is, we're going to derive it as usual on a set of coordinates that we have an intuitive feel for, because we have been used to those coordinates right from very early on, which are the Cartesian, rectangular Cartesian coordinates. So this is the same volume element, the control volume or system, if you want to call it so. Control volume has a fixed volume, system could change volumes. That's the only difference between those two terms. Let us take a control volume in the rectangular Cartesian coordinate space. This is x, this is y, right-handed Cartesian coordinate system. From x, you go from x to y, right-handed screw moves in this direction. Therefore, this is z. This is the cuboidal control volume. This is, let's say, x, y, z. The coordinates of this point are x, y, z. The coordinates of this point are x plus delta x, y plus delta y, z plus delta z. Okay. The same kind of the situation as earlier. Earlier, we saw mass moving in all three dimensions. We took each dimension separately. Here, we are going to see momentum moving in all three directions. You're going to see those as quantities, conserved quantities, of course. So the momentum flows into and out of the volume element by two major means that we have already seen. One is by convection or by virtue of fluid flow. The second one is by molecular aspects or by virtue of velocity gradients. Velocity gradients are the driving forces for that mechanism for momentum flux. Let us look at them one by one. We are, again to recall, we are doing a balance over a cuboidal element in a rectangular Cartesian coordinate space. Momentum moves in and out of that space. So first, by convection. We've already seen that rho v times v is the momentum flux. Mass flux into velocity, so that becomes momentum flux. I've already shown you how that happens. You can go back and look at it. When we did shell balances, I'd spent some time on this term to show you how this becomes momentum flux, and you multiply it by the area, you get momentum rate. Let me very briefly recall just the units, just in terms of units. The rate of momentum or momentum per time is area times AV times V. All these are vectors. A is the magnitude of the area vector. This is given as the magnitude of the vector. This is the symbol for the magnitude of the vector, absolute value. The magnitude of the vector times rho v times v is the rate of momentum flux. As I said, yeah, this is what I mentioned earlier. If you check in terms of units, area is meter squared, density is mass per volume, kilogram per meter cubed, velocity is meter per second, the velocity is meter per second. If you cancel out the various terms here, 2 will get on, 2 will go away here, and then one more will remain here in terms of m. Therefore, this will become m squared. Yeah, let us take this together as momentum. So, momentum rate, and what will remain here is meter squared at the bottom. You will get momentum flux. Also note that this is a vector, mass is a scalar, so it was much easier to deal with, and that's the reason why we looked at it first. It is a scalar, it is easier to deal with, it has an intuitive feel to it, you can easily relate to it and thereby pick up the principles and then move on to momentum. Typically, chemical engineers, aerospace engineers and so on and so forth do momentum balance first and then do the other balances. I have deliberately shifted this for this reason, for ease of understanding, ease of learning the material and so on and so forth at various levels. So, there are three components here to momentum, the x, y and z directions, and each of these components is composed of three other components. Just remember this, I will show you how this happens. For example, this is the convective momentum flux, or the momentum flux from the convective contribution, the bulk motion contribution. Area is a vector, rho, v vector, another v, okay, that we have already seen. This could have three different coordinates. This is the x coordinate, a magnitude, rho v, vx. This is the y coordinate, a rho v, magnitude, rho v, vy. And this is the z coordinate, area times rho v times vz. For short, this is the momentum in the x direction or x momentum, momentum in the y direction, momentum rate in the y direction, or y momentum rate, z momentum rate. Okay, this is the way we are going to call these things. Each of these has three components for vx, vy, vz here of this v, that is the one within brackets. For example, this one has three components, a rho vx, vx, a rho vy, vx, and a rho vz, vx. Similarly, this has three components. Similarly, this has three components. Therefore, you have 9 components for the momentum rate through convective means. We are going to consider only this to develop in detail, and once we write things for this, the other things we can write by extension. Okay, that will allow us to deal only with much less number of terms or much less number of equations to begin with, and that will make things much easier. And these are just extensions. Instead of vx you have vy, instead of vx you have vz here. So the same equations would be valid except for these changes here. Okay, so we are going to look first in detail at the x momentum alone. So x component of the momentum rate, we're going to later extend it. This is the same picture for visualization. The momentum rate due to convection, the entry is through the phase at x, through the phase at y, and through the phase at z, right? So the entry rates are in the x direction through the phase at x is rho vx at x times the area of the phase at x, which happens to be delta y, delta z, as we have already seen before in the case of mass flux. The entry rate at y through the phase at y is nothing but rho Vy Vx at y delta x delta z. That's the area of the face at y. The entry rate at z or in the z direction through the face at z, whereas the z phase, the z phase is this, the y phase is this. This is the phase at z. Is rho Vz Vx at z, at the phase at z, times the relevant area, which is delta x delta y. Let me write one exit rates and give you some time to write the other exit rates so that you'll get used to this process. It will also make things interactive. You'll learn much better. Exit rates in the x direction is through this phase, the phase located at x plus delta x. So that is going to be rho Vx Vx at x plus delta x times the area is going to be the same, delta y delta z. Now, I'd like you to stop the video, pause the video, go and write for the exit rates for the y direction and the z direction, and then let's compare notes. Go ahead, please. You would have obtained in the y direction, the exit rate in the y direction through the phase at y plus delta y, that is this, is nothing but rho Vy Vx at y plus delta y times delta x delta z, and z direction through the phase at z plus delta z equals rho Vz Vx at z plus delta z delta x delta y. Hopefully you would have gotten this. If there is some confusion, please write back to me. I'll answer, I'll clarify the doubt on a one-on-one basis. The net x momentum due to convection is nothing but the entry minus exit. So entry minus exit for each of these directions taken individually and then summed up is going to give us the net x momentum. Sorry, this is the net x momentum. The x momentum consists of all these terms. Therefore, the net x momentum due to convection is going to be delta y delta z rho Vx Vx at x minus rho Vx Vx at x plus delta x. And similarly, you have a term for the y direction component and the z direction. The x momentum in the y direction, the x momentum in the z direction. That's what it means. Okay, we are done with one term. Or I haven't shown you. Okay, we'll come to that in a little bit. Now the momentum rate by molecular aspects due to viscosity between the layers, due to the molecular nature, molecular interactions, and so on. Okay. That is given by the shear stress. And to understand this better, let us consider the force that is responsible for the shear stress. The force that is responsible for the shear stress is the shear force. The shear force acts on a surface. We all know this. And therefore, let us take the force that acts on the face at x. This is the face at x. The force that acts on the face at x is Fs at x. Okay, the surface force at x. Similarly, the force that acts on the face at y is Fs times y, which is y is here. Okay, y is here. This is the phase at y. The force that acts on the face is Fs at y. And the force that acts on the face at z, which is at the bottom here, is Fs at z. Okay. Each of these forces, these are forces, right? And each of these forces would have three components, x, y, and z components on their own. And therefore, we'll end up with Fs of xx as the x component of the face of the surface force at x. Fs xy is the y component of the surface force on the face at x. Fs xz is the z component of the surface force on the face at x. So these are the components of Fsx. Similarly, the components of Fsy are Fsyx, Fsyy, Fsyz, and the components of the Fsz or the surface force on the face at Z is Fsxz, sorry, Zx, Fszy, Fszz. Okay. Now let us divide these forces by the area of those faces, and if we divide the shear force by the area, you get the shear rate. So the shear rate, the corresponding shear rate are tau xx, tau xy, tau xz, components of tau x, tau yx, tau yy, tau yz, the components of tau y, and tau zx, tau zy, tau zz, the components of tau z. Okay. So we have 9 components for the surface forces or the surface stress, for the shear stresses that act on this volume element due to the from the x direction alone, or in the x direction alone. Okay. Also note that this superscript has a nice way of revealing itself. Tij denotes shear stress when I is not equal to j, and it denotes normal stress when I equals j. So tau xx is the shear force. We'll understand this a little better as we go along, but now understand this as a component, one of the components that arise. This is the x component of the stress due to the force in the x direction, or due to the component, x component of the force in the x direction. That's what this is. Don't worry about these details. As you get deeper and deeper, it will become a part of you. Okay, but pick this up very clearly. Don't once you pick this up clearly, then everything else is just methodically working things out. To repeat, we are looking only at the x direction, the momentum rate only in the x direction. That itself has three components, and those components are the ones that we are writing down. Both shear stress as well as normal stress arise due to molecular aspects. There is sometimes a confusion between pressure and normal stress. Okay, don't fall for that. They are two different aspects altogether. This normal stress arises due to molecular aspects. Pressure is separate. Pressure is a separate aspect. Just take it on face value now, and then whenever the confusion arises, remember this. You can add them. You can add them because they are in the same direction. The components are in the same direction. They become additive, but they are two different aspects. That's what I say here. Pressure is not related to shear or normal stresses. Let us consider only the x component of momentum due to the molecular aspects. What we have written here is all the components as we wrote for the convective component, convective contribution also. And we are going to consider only the x component, tau xx, tau xy, tau xz. And then by extension, we are going to look at these two. They become very simple extensions later. So this way, we need to worry only about 3 equations rather than 9 equations at a time, which can get confusing. The entry rates, again, we are looking at entry minus exit because we are going to substitute this in the momentum balance equation. So for the x direction is tau xx at x times the area delta y delta z. Y direction is tau yx at y delta x delta z. This is delta y delta z, this is delta x delta z. And the entry rate in the z direction is nothing but the shear stress times the area, the momentum flux times the area, that's the momentum rate. In this case, tau zx at z delta x delta y. The exit rates are, do you want to write them, or let me show you one, give you some time to write. In the x direction, it is tau xx at x plus delta x delta y delta z. Pause the video here please, and then write the other 2 terms, y for the y direction and for the z direction. Go ahead please. You would have obtained for the y direction tau yx at y plus delta y delta x delta z, and for the z direction tau zx at z plus delta z, delta x, delta y. Okay. So these are the entry and exit rates. So the net x momentum due to molecular aspects alone is entry minus exit. Therefore, delta x, delta y, delta z times tau xx at x minus tau xx at x plus delta x. Similarly, you have a term for the y direction, y component, and a term for the z component. If you recall the momentum balance, it was momentum out minus momentum in plus the sum of the forces equals 0 in the case of steady state, right? So we need the forces term. So the forces, what are the forces that we're going to consider? We'll usually consider two important forces that act. Any other force is not going to be a part of this derivation. In other words, this derivation considers only two forces. If there are additional forces, you need to go back to the derivation stage, add those forces at this stage, and then rederive the whole thing. They'll just be additive terms ultimately. It's quite easy to figure out, but for you to be sure, you need to add those forces here. The forces that we'll consider are fluid pressure and gravity, which will occur in many different situations. If you have an electrical force, if you have a magnetic force, if you have a surface tension force, and so on and so forth, you need to add it at this stage. So, since we are considering only the x momentum, let us look at the resultant force in the x direction. It is delta, the pressure times the area would be the pressure force. Pressure at x minus the pressure at the phase x plus delta x times the area is the same, delta y delta z. This gives us the pressure force, and mass times the acceleration due to gravity gives us the gravitational force. So density is mass per unit volume multiplied by the volume of the element, delta x, delta y, delta z. Therefore, this and this put together gives you mass times gx. Gx is the component of the acceleration due to gravity in the x direction. And also note that pressure is a function of density and temperature. Accumulation, okay, let's still keep the accumulation. Let's not put it to 0 as yet because we are trying to derive a general enough equation. Therefore, the accumulation on the right hand side of that equation in the x direction within the volume element within the system is nothing but the density times velocity times the volume divided by, the derivative taken with respect to time. So density times the velocity is momentum. So if density is mass per unit volume, therefore you need to multiply it by the volume to get mass, and then mass times Vx will give you the momentum in the x direction that is getting accumulated in the volume element. Dou t represents the time variation. So that is the accumulation rate. Now, the general momentum balance equation was what? 3.3.1, rate of momentum out of the system minus rate of momentum into the system plus rate of momentum accumulation in the system equals the sum of forces acting on the system. This we took together first for the convective component and then the molecular component. This we saw next, sum of forces, and we have a term for this. We just go and plug those various terms into this, and that's all there is. We are doing a momentum balance. We just split those various contributions, and they were available in an easily understandable form in terms of the variables that can be measured. They were written in terms of the variables that can be measured. And now we are putting them back into the overall fundamental momentum balance equation, second law of motion, Newton's second law of motion. If we do that, and our usual trick, you divide by delta x, delta y, delta z, then take the limit as delta x tends to 0, delta y tends to 0, delta z tends to 0. Okay, why don't I ask you to pause the video here. This is the equation that we are interested in. We have already gotten this term separately, this term separately, and this term separately. Why don't you go and substitute these terms, divide throughout by delta x, delta y, delta z, then take the limit as delta x tends to 0, delta y tends to 0, delta z tends to 0, and see what you get. Okay. Then of course we'll compare and see whether you got whatever you're supposed to get. Okay. Pause. Go ahead, please. Hopefully you would have gotten dou rho Vx dou t equals minus dou x of rho Vx Vx plus dou y of rho Vy Vx plus dou z of rho Vz Vx minus dou x of tau xx plus dou y of tau yx plus dou z of tau zx minus dou p dou x plus rho gx. Okay. This is what you'd have gotten for the x momentum when you substituted it. So this is the momentum balance for the x momentum alone. However, this is a three-dimensional situation, as we said. It has three different components. We can write the other components by just extension. You can go and check yourself, do the whole thing again for the other component and see whether you get this. But you can take it from me that it is just going to be an extension. Therefore, for the y direction, it's going to be, before that the x direction equation is 3.4-1. The y direction would be dou rho Vy dou t equals minus dou x of rho Vx Vy plus dou y of rho Vy Vy plus dou z of rho Vz Vy minus dou x of tau xy plus dou y of tau yy plus dou z of tau zy minus dou p dou y plus rho gy. This is equation 3.4-2, and we have a similar equation in the z direction with the appropriate velocities and shear stresses put in. Okay. This is equation 3.4.3. So all these three equations put together is the overall momentum balance equation of motion, or you can call them equations of motion in these various directions, right? This is the equation of motion. In compact terms or vectorially, we can write this as dou t of rho v vector equals minus del dot rho vv minus del dot tau minus del of p plus rho g. Okay. Equation 3.4-4. I think we need to take a break here. We've been at quite an intense derivation for quite a long period of time. Let's take a break here, I think, or before that, let me say what these are. This is nothing but rate of increase in momentum per unit volume in the control volume in the system. This is rate of gain in momentum by convection per unit volume. This is rate of gain in momentum by viscous effects per unit volume. This is pressure force on the element per unit volume, and this is gravitational force on the element per unit volume. Okay. So these are the various terms that come together in momentum balance in this relationship. Yeah, let's take a break here. When we come back, let us continue with some more aspects of this equation of motion. There's a lot of insights to derive from this equation of motion before we start applying this. There are a lot of things that I've left hanging there. There were 9 terms. What kind of a quantity is that? Okay, those things we will talk about in some detail in the next class. See you then.